Yes. Okay, I'm just showing you right now. I'm right here in Indiana. I'm in southern Indiana at the moment. And maybe I'll zoom back in. And then tomorrow I get on a train and I go from Indianapolis to Boston all the way via train tomorrow. And then I go back all the way from Boston. Whew, that's too far. And I go all the way from Boston back to Montana, to Browning, Montana, in 1 week. Okay, so let's do the batteries quiz.
I sent it to you.
Say again, please.
I sent you.
Oh, yes. My pleasure. It's been a long trip. So I've been traveling for 2 or 3 weeks now, and I have 3 weeks left. I have to go to Boston for 2 weeks and then Browning. So, are you all excited for your visit to see John Bailey?
Yes.
I think it's going to be great. Okay, well I'm going to go through the batteries quiz. Is that okay?
Yeah.
Okay, super. Okay, tell me if I need to slow down or if you have another question, but I thought I would just go through each question.
Okay.
Okay, so this is the battery quiz, and the question is, it says, it is unwise to add new batteries to an established bank. And
Which one?
yeah, I think, because what ends up happening if you have batteries of different ages, they have different charge and discharge characteristics. And if one battery has a lower voltage than another one, then and I'm sorry I don't have my pad today. I don't know my journal.
Okay, have you sent me this quiz?
Oh, I thought you did not do this quiz already?
No, I had TV curriculum review paper.
Oh. Okay, let's take a pause then. Okay, I think we're back. I have inverters, and I am also recording. All right. So this one, it's topic 8, inverters. And again, just to remind you, let me get a new. Oh, no, I'll just write right on here. Okay, so remember, inverters convert DC to AC. Also, rectifiers convert AC to DC. So it's critical that you remember that inverters convert DC to AC. Okay, so that's the most important thing to remember here, because a lot of appliances run on AC. Okay, so the next thing, the question is, a blank wave is an alternating current waveform that switches between maximum positive and negative values every half period. So the answer is alternating. And the other thing to keep in mind is that the the current looks like this. So if you have a waveform, so if this is time and this is voltage, the current goes between positive and negative. And the other thing to keep in mind here when we go, if you want to do some research on this, there was a very famous argument between Tesla versus Edison, AC versus DC. So if you go back here, this is kind of interesting here. You can see the war of the currents, AC versus DC power, and the Department of Energy is probably a good place to look. So Thomas Edison said we should do DC, and Nikola Tesla said we should only do AC. And the reason that Tesla won is because an AC current can travel much farther without losses. So all of these big power lines we see are all AC power. But the electricity that comes from solar panels is all DC. So you can do a little bit of research on that. Okay, so alternating is the correct answer. All right, so this next one, a blank module. There's a D missing there. A blank module is a
we get answer C.
Number 3?
Yeah.
Okay, I'll show you that one. Okay, a blank module is a P.
We get
I'll show you number 3 shortly. Okay, a blank module is a PV module that outputs AC power through an inverter attached in place of the normal DC junction box.
Uncle,
Yes.
what is the answer? Second.
Oh, sorry. Ask me one more time.
What is the answer to second quiz?
The second question?
Yes. We get DC.
This question?
Yeah.
Yeah, this is a good one. Let me see. A blank module is a PV module that outputs AC power through an inverter attached in place. You know, I think it's just going to be this guy. I think it's just going to be an AC module. Typically, what we'll see. Let me show you something. The key here is a micro inverter. Micro inverter. And let me show you a micro inverter. Yes.
What meaning DC?
Yeah, let me show you. This is just a good image of a micro inverter. So in this case, each panel, this is DC, 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 but each panel has its own inverter. So inverter, inverter, inverter. So each panel, rather than sending DC electricity, each one sends AC based, right at each panel. So each panel is making AC. So the whole set is making AC current rather than the DC panels being wired in series. So That's what we're looking for right here, are panels that each have their own inverter. It's becoming much more common. So I don't know what you might also see. Well, I don't know what a converter panel is. Let's just see if there's something like that. Converter. That might be a term. I'm not familiar with it, but it could be. Yeah, I don't know the word converter. So let's just go with AC, and then let's also, the thing to remember is micro inverter. That's the key word. It's definitely not DC, and it's definitely not rectifier, because those both are, because if you remember earlier I said rectifiers convert AC to DC. Okay, so the next one, harmonic distortion in a modified square wave. It definitely causes extra heat in motors. It definitely causes extra heat in motors. It's not a phase shift because it's still in phase. It would not be a current imbalance because all the current is still moving through, and it would definitely not cause a power factor of 1. It would actually cause a power factor of less than 1. Okay, so number 4, blank is a device that transfers energy from one circuit to another through magnetic coupling. This is a transformer. Let me show you. Transformer. These are actually quite cool devices. So what you see in a transformer is that you have current coming in, and so the current is flowing, and we've studied this before, and it travels in a coil or a helix or a set of loops. And as it travels, the voltage drops. The voltage drops here, and since there is electricity, you also have magnetism. So the magnetism is always perpendicular to the electricity. So the electricity is flowing horizontally in a loop, and the magnetism is flowing vertically right here. The other thing to keep in mind is that the magnetic field is always itself in a loop. So this iron keeps the magnetism local. It keeps the magnetism from leaking. So it stays here. The magnetic flux is flowing in this direction. And what happens is it causes secondary current. So you can see there are fewer loops here. And then I'll show you the equation. Here's the critical equation. So you can see this is the voltage in the primary and the voltage in the secondary. So if we go here, here's the voltage in the primary and the voltage in the secondary. And then over here, this is the number of loops in the primary, the number of loops in the secondary. So if the voltage in the primary goes up, the number of loops has to go up also. So here in the primary we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. in the primary. So in this case, let me just show you. NP equals 15. And then if I go back 1, 2, 3, 4, 5, 6, 7, 7, N secondary equals 7. So then we go back to our equation, and we can see that VP over VS, VP over VS equals, actually let's just say this is 14. It's just easier. 14 over 7 equals 2. So the voltage drop in the primary is double. So since we have more loops, there's more voltage drop. But the other thing to keep in mind, and this is very important, is that the power in the primary equals the power in the secondary. So we know that the voltage in the primary times the current in the primary equals the voltage in the secondary times the current in the secondary. So now we since we know that these two are equal, we can say that 2, so the voltage in the secondary, so from this we can just write it like this. The voltage in the primary equals 2 times the voltage in the secondary. So if we come up here, we can say 2 times the voltage in the secondary times the current in the primary equals the voltage in the secondary times the current in the secondary. And then we can cancel the voltages, and we can say that 2 times the current in the primary equals the current in the secondary. So in this case, the voltage in the primary is high, and the current in the secondary is high. This is very important. It's fundamental physics for AC current. Very important. Sorry I'm writing so slow, my tablet died. Very important. Okay, so these are transformers. So if this, what it's saying is if this voltage is high, then this current is high. So if this voltage doubles, this current doubles. So the transformer is a way of maintaining power but dropping the voltage. So this voltage becomes safer. Okay. I like that question a lot. All right. Blank is the shape of an electrical signal that varies with time. This is the waveform. It's the waveform. So if I go back here, I I don't think I ever finished this. And maybe you know this from your math already, but the waveform looks like this. And I also suggest, so this would be a sine wave. Sine wave, and if I do a different color, if I go here, 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 here. Now I'll do a cosine. This is a cosine. So that's the sine, and this is the cosine. And you can also see that this is 0. This is pi by 2, or 90 degrees. This is pi, or 180 degrees. This is 3 pi by 2, or 270 degrees. And this right here is 2 pi, or 360, and back to 0. So this whole thing is one cycle. We go up to 1, back down to 0, down to -1, and then back to 0. That's the sine. And then the cosine is 90 degrees out of phase. 90 degrees different. So this is also fundamental. And these are sinusoidal waveforms. You could also have a square wave. Square wave. So if this is time and this is amplitude, you could have a wave that goes like this: flat, down, flat, over, flat. And typically what you'll see, so this is square. Square wave. All right, and then what I'll show you, this is also important for inverters, is if we go and look at a typical inverter, modified sine wave. Let's just look for an image. Okay, this is a good image. So usually, since all of these inverters are, they're partially analog, they're partially digital, this would be a perfect sine wave in blue. That's usually what you want to see in your electronics. But what you usually get with an inverter is a modified sine wave. And this causes distortion and heat and things like we said before. So this is more of a digital signal, but it's an approximation. Okay, waveform. So the waveform, this is the shape of the wave. Sine, cosine, sinusoidal. Sinusoidal is the shape, and a cosine is sinusoidal. A sine is also sinusoidal. Square, triangular, modified sine wave, etc. Okay, the key is that the waveform is the same as the shape. Okay. Next question. Phase unbalance in the phase unbalance is the unbalance that occurs when three phase lines are more or less than 120 degrees.
Yeah.
Yeah. Let me show you that. That's a fun problem. Let me show you. I'm going to show you how to do this in Microsoft Excel. It's fun. Have you ladies been using Microsoft Excel at all? If you haven't, I encourage you to. So let me do this quick problem here. 0, 1, 2. I'm gonna draw some sine waves. I'll keep it very simple. I'm going to convert this to sine and cosine, and I'm going to show three separate phases. So here's numbers, starting from 0 to 20, and then I'll go. This will go from 0 to 2 pi, 2 pi. So equals this number times 2 times pi, and pi will be a function, and I'm going to divide that by 20, which is the final number, and I'm going to pin it to that same cell. Now let's see what happens. Okay, I think that's pretty good. Now let's do the sine equals sine, or just sin, of that number. And we'll drag this. Okay, that's good. And now I think what I'll do is shift it a little bit. So I'll put the shift over here. And I'll let this equal 2 pi divided by 3. So we're just going to do a phase shift. So I'm just going to call this sine 0. And I'm going to call this sine 120, which is a third of a phase shift, because 120, actually I'll put one more number in here so you can see the degrees. This will be the degrees. So equals 0 times 360 divided by 20. I'll put a dollar sign in there, and I'll drag it. And these are degrees. And this one, I'll just label this as radians, because that's what it is. And somewhere between 6 and 7 is 120. I don't have that exact number here, but 1/3 is about right here. So 6.66 is 1/3. Okay, so now we'll do sine 120. So this equals the sine of this number plus that number, which is a shift. And and I'll pin that right there too. And now I'll drag it. And now I'll do sine 240. This, I'll just do this shift. I'll just call this shift 1/3. And I'll call this shift 2/3. So equals 2 radians times 2 divided by 3. So this number 4.1 is down around 2/3. So this number, the 1/3 is about here. The 2/3 is about here. 240 is somewhere in here, and 120 is somewhere in there. Okay, so this equals the sine of that number plus this number, and again I'll pin it. And I'll drag it. Alright, now I'm going to plot it and see what happens. Insert, charts, plot. Oh, almost worked. Let me see. Didn't quite get that. Okay, this one looked good. That's my sine. Let me see what I did wrong here. Let me see what I did wrong here. That's fun. Enter. Let me see. Give me 1 second. I'm going to pause. Sorry, I made a mistake. Okay, tell you what. I'm gonna come back to that one. I'm gonna come back to that one. Let me go back to the quiz because I need to figure out where my error was. But okay, so I'll show you. This is also important because it's a 3-phase line. I'll show you what I was trying to draw here. 3-phase power. Yeah, this is what I'm showing. I was trying to get fancy and draw this in Microsoft Excel, but here's red, yellow, and blue. And
we couldn't see your video, Uncle.
Oh, you can't see the screen again?
Yeah.
Okay, let me stop sharing, and I'll go back.
Okay.
Okay, let me start again. I think I just need to go back. Share screen, full screen. Okay, so now I'm trying to show this red, yellow, and blue. You can see that now, 3-phase supply system.
Yeah.
Okay, so this is 3-phase power, and you can see that the shift is 1/3 pi, and that's what I was trying to do in my graph. I messed something up a little bit, but you can see that each one, this one starts at 0 and goes up. The next one starts at 2/3 and goes up. The next one starts at 4/3. So this is basically 0, 60, 120, 180, 240, 360, all the way back. So This is three-phase power, and typically this is used for motors, for motors, and it makes the power much smoother. So that's what this question was asking. So three-phase, each one is 120 degrees different. Then I did something wrong with mine, but I'll fix it. All right. Blank are temporary, undesirable voltages in a circuit ranging from a few volts to several thousand and last for a few microseconds up to a few milliseconds. And these are transient voltages, or voltage spikes, or voltage spikes. And they can cause damage. And these are typically fixed with capacitors. And we covered capacitors last time. Typically fixed with capacitors. Okay. Next question. Blank is the measure of how closely the power on an electrical circuit matches the nominal values from parameters such as voltage, current, harmonics, and power factor. That's power quality. How high the quality is. Yeah. These other things don't have any, don't make any sense. Power quality. All right, next one, number 9. The blank is not an acceptable location for a grid tie inverter. That's correct. Not acceptable. Because then it's could be damaged. By sun. So the north side here, it's protected from sun and rain. Same thing here. It has to be protected. Okay. All right. The next one, frequency at a typical outlet, 60 hertz, 60 cycles per second. I think that's true in Sri Lanka. Let's do some research. I don't know. AC power frequency in Sri Lanka. Oh, look at that. 50, that's what I thought. Yeah. 50 in Sri Lanka. Yeah. This is true. This is true in Europe. Yeah. This is good. Let's look at this. List of worldwide AC voltages and frequency. I don't know who Ron Curtis is, but it looks like he's done a little bit of research. Yeah, this is important. Most countries use 50 hertz. Only a handful use 60. The U.S. uses 60. So let's go back. United States. Well, let's go down here, make a new answer. E, 50 hertz. And most of the world. The United States is a little different, a little funny, a little backwards. I think if we go down here, we'll see India. Here's India. Yeah. Look at that. So there's India. Here's the United States. 60 hertz. Okay, that's a good question. Now we know the answer. All right. Blank is the number of waveform. Blank is the number of waveform cycles in 1 second. It's the frequency. So let me draw that. If we go back here, let's just do another sine wave. And if this is time, and if we go back to the page, if we go back to India, we see the voltage is 240 and it's 50 hertz. The number here is 240 volts. And if this is time, and if we start here, we go up to 240, we go back down to 0, we go to negative 240, and we go back to 0. So this is 0. This is negative 240 volts. From here to here is 1/50th of a second. So very short time. Oops. So 1 divided by 50 equals 0.2. 0.2 seconds. So 0.02 seconds. Or this is 0.01 seconds. All right, and that's called the frequency. Frequency. Get bigger. Frequency equals 50 hertz. HERTZ equals 50 Hz, the other way, equals 50 cycles per second. So the signal goes from positive, it starts at 0, if you like, if this is a sine wave, goes up to 240, back down to 0, back down to negative 240, and then back to 0 every 0.2 seconds. So the frequency equals 150 equals 50 hertz, 50 cycles per second. All right, that's how the AC works on the Sri Lanka grid. A MOSFET. This is a transistor, and let's just go look it up really quick. These are kind of fun. MOSFET.
No.
MOSFET. Okay, so really what happens in the transistor is if it gets a small voltage, it allows current to flow. So think of it as an electrical valve. So when the gate voltage changes, current can then flow. So when it says field effect means when the electrical field changes, so the voltage changes, the current can flow. So it's a switch. So this is yeah, it used to be called metal, but really they're no longer used in metal. It's usually polysilicon, and we've covered silicon in the past. And they're typically small, and they're used in switching, and these are the transistors that are actually creating those sine waves that we saw before. And they're typically the things that break or burn out when your inverter dies. Okay, transistor. All right, number 13. Blank are the power required to operate inverter electronics and keep the inverter in a powered state. Ratings. These are the standby losses. Standby losses. And maybe we should change this. Are the power requirements. The power requirements. And this just sort of keeps it alive. It's sleeping. Think of it like sleeping, but still using energy. Okay, number 14. Grid tie inverters are sized by the array, the battery, steady state, or the AC distribution. So the bigger the array, the bigger the inverter has to be. We can discuss that too. It's also determined by this. If the panel main breaker is large, the inverter needs to match it. They need to be comparable sized. So both of these are the right answer. It's not battery because this is typically for off-grid. Steady state and surge loads, this is also true. So there are many factors here to consider. Okay, the next one, a blank commutated inverter is an inverter that can internally control the activation and duration of its switching. So this is a self-commutated. And I'm going to let the electricians cover this one. This is something that's a little bit outside of my specialty. Okay. The peak voltage of the waveform at a wall outlet, this is 120. But if we go back, let's go back here. If we go to India, it's going to be 240. So you can see in the US it's down here at 120, but the India, and I assume Sri Lanka has the similar standard. We go back here. This is for US. E 240. Okay. All right, here's the next one. Most inverter manufacturers provide string sizing. So this is a string of modules to show their recommended configurations, number of modules in series, and number of strings. You still need to do the calculations yourselves. These calculations are important. Okay, so here's an example to practice on. So the inverter is an SMA SB 3000. The modules are REC 240s, and the location is Missoula. So it says find the following values on the equipment spec sheet and record them here. Okay, I think, all right, so we need to find the maximum DC. So let's find the SMA. I believe this was in an email, so let's go back and find that. Oh, here's a question from John. Reply to all. Yes, we are working through it. All right, so I'm going to keep going here. I'll keep going here. Okay, so we need to go find that inverter. I'm going to take a break and then I'll find it. So right now I am saving the Sunny Boy manual, and I'm also going to go and search for the REC module. Solar Design Tool. And 240 means it's 240 watts. And here's the manufacturer data sheet. So you'll want to download this also. Uh-oh. And you can just grab one of these. See if we can find one. Specifications and product info. And we'll get it in English. Oh, there we go. 2 pages. Ah, and I think everything's here. So there's the temperature coefficient. Here are the open circuit voltages. And here are the short circuit currents. So download this. Download this. So this is the REC 240. Save it. Yeah. Okay. So that was a lot. So for this last problem, you can download the specs for the inverter and download the specs for the panel, and then fill in those last bit of that last bit of information, and then send it to me. Okay?
Okay.
All right, ladies. All right. Thanks so much. Thanks for your patience.
Bye.
Bye-bye. Bye. Okay.